So moving on from glaciers, let's look at a little bit about ecosystem changes that have happened, are happening, and are expected to happen because of global warming. There is a concept of regime shifts or tipping points in the system that I'll come back to a little bit later on. But typically we look at forests and indicators of any switch to a situation that will not come back. So there is hysteresis which comes back in a different pathway if you perturb a system and then try to conditions change in a way where you are, let's say, building a glacier and melting a glacier. We said the pathways are very different, but there are also tipping points or switches or thresholds where the system jumps to a new state which will not come back, at least not in it will take geologic timescales to return, let's say. Okay, such things have happened, especially when we looked at long timescale paleo changes going from the time of the dinosaurs to the present. Obviously we've changed temperatures in the Arctic region by more than 10 degrees centigrade, where Arctic used to have lush green forests. Mammoths and dinosaurs were running around. Arctic ice, Greenland was vegetated, Siberia was vegetated, and so on and so forth, and now we are in a new state, right? So this is tundra here, a biome at far northern latitudes characterized by grasses and shrub vegetation and permafrost beneath the seasonally thawed soil. So permafrost is basically permanently frozen soil. So at the seasonal time scale, the top of the layer may thaw or melt, and then it refreezes. So the depth of the permafrost or frozen soil is very critical, and of course with climate change the seasonally active layer can get deeper and deeper. Why do we worry? Because permafrost, when soil freezes, it also freezes organic matter, carbon dioxide, methane, and so on. Obviously it can get warmer and start to release CO2 and methane and lead to a positive feedback. Okay, so musk oxen, geese, caribou, Arctic fox, Arctic hare, snow owl, and lemmings are some of the animals that inhabit Arctic tundra. Miserable cold weather with very little food, but they have evolved to survive. Warming here can switch the system to what is called taiga, or known as boreal forest full of pine trees. You can see the difference here. These are now at lower latitudes, so the biomes are shifting northward. There is already evidence of this happening, and there are details that ecosystems don't move. So if you look at a combination of species that exist in the current climate, when climate warms along, let's say, latitudes or up a mountain, entire ecosystem doesn't move. There are species that are mobile, that are generalists, which can quickly move, and there are species that are specialists, sedentary, and they are not able to move. So species begin to change, the composition of ecosystems begin to change as well. But in general, the character of taiga or tundra or boreal forest versus tundra are going to be very different. So here are some projections. Potential vegetation is kind of a counterfactual world where, given the climate conditions, if human beings didn't have an influence, what would be the vegetation? So these are the types of vegetation here. Ice, tundra, this is the UA is tundra and alpine, BC is boreal conifer forest, temperate conifer forest, temperate broadleaf forest, temperate mixed forests, and so on and so forth. I won't read all of them, but you can see how potential vegetation should have looked in 1990, and projected changes in potential vegetation from 1990 to 2100 from this paper looks like this, and you can see massive changes in some regions here in terms of the potential vegetation by 2100, including even in the deep tropics. You can see the Amazon, Central African forests, large parts of India are going to be seriously affected, also over China. But remember, this is potential vegetation. Already agriculture is made massive changes in the potential vegetation. So how much confidence do we have in biome changes? So this shows that there are some places where the confidence is very high, and there are other places where the confidence is not that high. So the changes here are pretty big, but the confidence in these changes is very small. Similarly here as well. Okay, so uncertainties remain, but how do we think about it? I'm not going to get into it right now, but obviously this is a risk we are facing. So you can say, well, we don't have much confidence and not do anything, or you can say, wow, this is a massive potential risk, so what can be the solution? So how we react as individuals and as a community and as a species is going to depend on how we perceive risk, and this is the biggest part of the climate debate, of course. Okay, so the climate change and vegetation also includes projected changes in the number of days exceeding 93rd percentile of the fire weather index, FWI, by the mid 21st century, so 2041 to 2070, under the high emission scenario business as usual RCP 8.5 that we talked about before. Dark red shading indicates the largest increases, while the pale green shows small decreases. Red triangles, some big noise here, I'm not sure what it is, maybe some bird. Anyway, extreme. So basically the point is the climate change impact on forest fires, wildfires is complicated because humans manage systems, plus area burned may not necessarily increase, but the number of fires and the intensity of the fires is changing, and there is a positive feedback. If you warm, there is a soil moisture loss, vegetation dries up, vapor pressure deficit drives forest fires, and so on and so forth. Of course, the sad part of the ocean impact also includes bleaching of the coral. So this is a healthy coral and this is a bleached coral. During El Nino, for example, when the warming happens, there is natural bleaching. The question is how quickly do they recover, and whether global warming is delaying the recovery from the El Ninos. So Great Barrier Reef is being watched very closely. A lot of actions are taken to protect it, including making it a UNESCO heritage site, and there is some report just came out saying some of the corals are showing signs of recovery. So we talked about acidification. This is a direct consequence of warming and acidification. Okay, there are also ideas that narwhals are going to be replaced by killer whales as they keep migrating into higher and higher latitudes with warming, sea ice loss, and so on. Climate change in general affects human health as well. So I'm going to just include this into, actually maybe I should leave it, the ecosystem, and come back to human health in the next podcast. So to compensate for the last podcast, which was very long, I'm going to make this a little bit shorter. But vegetation feedbacks are very complicated. In the models, the simulations are done now that many models have dynamic vegetation modules in them. You can make climate change impacts without having vegetation and carbon feedbacks, and you can make another simulation where you allow the vegetation to respond to climate change, temperature change, precipitation change, vapor pressure deficit change. What is vapor pressure deficit? Basically, it's the amount of water that atmosphere can hold at that temperature versus what is actually present. Why does it matter? Because leaves have to open their stomatas to capture CO2, but they want to open it just long enough so that they don't lose the valuable water that they have moved up to the leaf from the root systems. With CO2 increase, the stomatal conductance can be changed, because high CO2 means they don't have to remain open for too long, so CO2 can be captured quickly. But the warming can also mean vapor pressure deficit increase, which means the vapor loss can increase even with a shorter opening of the stomata. So complicated feedbacks happen. There are also soil moisture feedbacks, and there is some evidence that certain species can actually exacerbate the droughts because of the way they respond to warming and drought and vapor pressure deficit, and so on. So this is still a very active research field. Models are improving in details and understanding, and they are making projections with and without feedback. Because remember, carbon cycle feedback means if vegetation biomass changes, then sequestered carbon in the vegetation biomass changes, so that will have impacts on the CO2 that remains in the atmosphere, which then feeds back to the warming, and so on. So you can see how complicated it gets. Okay, so we will leave it there for now.